So, good morning, dear students. So, we have done the Lindberg failure theorem, which is one of the famous theorem in central limit theorems, and that theorem gives a necessary and sufficient condition for an independent sequence of random variables, for a sequence of independent random variables. Now, we will discuss two corollaries about the theorem. So in corollary 1, which says that variance of Sn tends to infinity under Lindberg condition. So it is very easy. Now the proof is that suppose the Lindberg condition holds, and if variance of Sn tends to some real number c, then we would have limit of the maximum sigma k square by variance Sn maximum over k in the range 1 to n. This is greater than or equal to limit sigma 1 square by variance xn, because this is the maximum one. So if we remove the maximum, then this will be larger. This is the maximum, and instead of sigma k square we have sigma 1 square here, because we put sigma 1 square instead of sigma k square simply because in order to have this inequality, this is the maximum. In order to have the maximum, and this is only maximum of all those sigma k squares, instead of that we simply replace it by sigma 1, so this will be larger. So this is equal to sigma 1 square by c if variance Sn tends to c. Okay, so this is not equal to 0 because c is some real number. Sigma 1 square is finite non-zero variance of x1. So this contradicts the condition number 1 of the theorem. So we should not assume variance Sn tends to c. Instead, we should assume variance of Sn tends to infinity as n tends to infinity. So very simple logic, the proof of this theorem. In corollary 2, what we say is that let xn be a sequence of almost surely uniformly bounded. Almost surely uniformly bounded is the condition here also. So almost surely uniformly bounded independent random variables. So this is the condition. Then Lindberg condition holds if and only if variance of Sn tends to infinity as n tends to infinity. So the only if part is corollary 1. The only if part is that when we suppose that Lindberg condition holds, then variance Sn tends to infinity. So the if part is conversely suppose variance Sn tends to infinity, then we have to prove that Lindberg condition holds. Now since Xn is a sequence of almost surely uniformly bounded, there exists a real number a, positive real number, such that probability of absolute Xn is less than a is equal to 1. So the meaning of almost surely uniformly bounded here for all n. So if mu n denotes the expectation Xn, then mu n is less than or equal to a, because probability of absolute Xn less than a, so the mean will be less than or equal to a. Absolute the mean will be less than or equal to a. All the Xn's are less than a. Their average will also less than or equal to a. So this implies that absolute Xn minus mu n is less than or equal to twice a. This is the absolute. So one a is from Xn, another a is from mu n. Okay, so combining this Xn less than a and mu n less than or equal to a together implies this absolute Xn minus mu n less than or equal to twice a, almost surely for all n. Okay, this is question number 2. Now fix epsilon, a positive quantity. Then since variance Sn tends to infinity as n tends to infinity for sufficiently large n, so this one, for sufficiently large n, and k less than or equal to n, we have absolute of x k minus mu k less than or equal to epsilon square root of variance of Sn. So variance of Sn is a quantity which tends to infinity. So we can choose n sufficiently large so that this quantity is larger than this quantity. Actually, this quantity is less than or equal to twice a. We have already shown in equation number 2 that. So if we choose n sufficiently large, this quantity could be made larger than this quantity. Question number 3. It follows from equation number 3 that for sufficiently large n and k less than or equal to n, integral in this set of x minus mu k whole square df k is equal to 0. Because you see this set is now become a null set because of 3. Here almost surely this xk minus mu k less than or equal to epsilon times square root of variance Sn. So if you reverse this here, greater than epsilon square root of variance, this set, probability of this set will be 0, indicating that this is a null set. So integrating in a null set of any integrand will be 0. Okay, so you see in the condition number 3 of the Lindberg failure theorem, in the condition 3, what do we write? This integrand before this integral we write limit 1 by variance Sn. So if it is 0, then whatever put in before the integral will be 0. So Lindberg condition holds. Okay, this much for today. Try to understand these two corollaries. Stay safe, stay home. Have a good day ahead.